Hello everyone, welcome back to another video. In this video, we're going to be doing an introduction on index notation. So we're done with quadratic equations, and I'll basically be discussing what an indice is, how to interpret a base and an index to write a term in expanded form, how to expand indices, and how to factorize indices. And I'll be going through some laws of index notation. So to start off, we need to discuss what is an indice. What are indices? So to give an example of an indice, I'm sure we've all seen something like 2 to the power 3. Well, 2 to the power 3 is essentially 2 times 2 times 2. That's basically what an indice is. So indices are basically a shorthand way of representing repeated multiplication of the same factor. So it's basically repeated multiplication of the same number. So here we're multiplying 2 multiple times, so it's being multiplied by the same factor. So that's what an indice is. And let's just look through some of the functions in what an indice is. So let's say we have a number 2 to the power 5. So what is this 2 and what is this 5? Well, the 2 is what we call the base. Okay, so the base is basically the factor in the product that will be repeated through multiplication multiple times. And now this 5 here is the index. So it's the index. And this 5 is basically the amount of times we will multiply the factor. So this 2 to the power 5, that would essentially be 2 times 2 times 2 times 2 times 2. So we have 2 multiplied by 5, 2 multiplied by itself 5 times. And let's, if you notice through this logic, we can also see an example such as 5 to the power 1, that equals 5. So therefore, a to the power 1 equals a. So any number multiplied to the power of 1 is just itself, because it's not being multiplied by another number. So so that's one law we've already got. So I'll just write index laws here. And our first index law is that a to the power 1 equals a. Now, another thing we need to mention, what if we have something like 2, I should just rub this off, just wait. So let's say we have a question like 2 to the power 2 times 2 to the power 3. What would this equal? Well, we can obviously evaluate it one by one, but this also leads us to another index law, and that is a to the power m plus a to the power n equals a to the power m plus n. So what that means is, whenever we have the base as the same thing that are being multiplied, we add the two indexes. So this would basically equal, the base would say that's the same, but then we would add the two indexes. So it would be 2 plus 3. So that would obviously equal 2 to the power 5. And then we can evaluate from there. So that's another index law. So we've gone through what happens when indices with the same base are multiplied, but what if they're divided? So let's say we have something like, this brings us to another index law, and that is a to the power n divided by a to the power n. That equals, well, if a to the power m times a to the power n equals a to the power m plus n, that means this would be a to the power of m minus n. So that's one other law. So if we have the example 4 to the power 3 divided by 4 to the power 2, this would essentially equal 4 to the power 3 minus 2. So that's another index law. Let's try something else. Let's try something a bit more complicated. So let's say we have 3 to the power 3, and then on top we have 9 to the power 3. Well, you might say, oh, hang on a minute, these bases aren't the same, so they cannot be, so we cannot use one of the index laws. Well, actually we can, because this 9 to the power 3 is same as 3 squared times 3. That's the same as 9 to the power 3, and then here it would be 3 to the power 3. So 3 squared times 3, we know that these two are being multiplied. Actually, I probably should have wrote it a bit better. Just wait. This may seem a little bit confusing, but I'll explain what I mean. So like 3, so 9 can basically be said as 3 to the power 2. If we put that in brackets and then we cube that, this leads us to another index law, and that is a to the power m to the power of n equals a to the power of m multiplied by n. So whenever we have this kind of format, the two indices actually multiply each other. So 3 to the power 2 times to the power of 3, that would be 3 to the power 6. So now we can do 3 to the power 6 divided by 3 to the power 3. We know that equals 3 to the power 6 minus 3, which equals 3 to the power 3, which equals 27. So that's how we get another answer. So those are some of the fairly basic index laws. And I hope you noticed how I got 9 to the power 3 to 3 to the power 6. That can happen a lot. And now that we've gone through some of the index laws, let's look at how to get expanded forms into an index form. So let's say we have something like 4 times 4 times 4 times 4 times 4. The first thing, this is clearly an expanded form because it's multiplying by itself. So now we can, the first thing we have to do is how many times 4 is being multiplied by itself. So there's 1, 2, 3, 4, 5. So that means it's multiplying itself to 5 times, so that means it will have a power of 5. And then we have to check out the base that it's being multiplied with, and that is 4, because 4 is being the repeated base. So our answer would then be 4 to the power of 5. Okay, let's try something else. A bit more different this time. How about 4 times 4 times 4 times 3 times 3 times 2. Now this one is going to be a bit different, because now there's different bases, but still it shouldn't matter. So in these kind of circumstances, we still need to count how many of every single base is being multiplied by itself. So the first base we have is 4. How many times is 4 being multiplied by itself? 1, 2, 3. So it's being multiplied by itself 3 times, and that means it will have a power of 3. Next, we multiply that with, because that's a multiplication sign. How many times is 3, the second base, being multiplied by itself? 1, 2. So that means it will have a power of 2. And then times, how many times is 2 being multiplied by itself? It's only being multiplied by itself once, because it's the only number there. So this one would be 2 to the power 1, which is also just 2. So that's another way we can get it into index form. Now that we've gone through index notation, we're going to go through something that is called prime factorization. So I'll just write the heading. Prime factorization. So prime factorization is basically involving a number as a product of its prime factors. So prime factors would include 2, 3, 5, and these are because they can't be divided by any number except itself and 1. So let's say we have the number 108. We have to involve writing this number as a product of its prime numbers. So the answer of 108 is prime factor form is 2 squared times 3 cubed, and I'll show you how we got there. So the way we start writing it in prime factor form is we have to check out how many times what can 108 be divided by when it's divided by 2. So we have 2 here. 2 is a prime factor, so we already have that, and 2 and 54, because 2 times 54 can be multiplied to give 108. So we already have 2 as a prime factor, so we can't divide that anymore. So we have to see how many times what answer we get for 54 when it's divided by 2. So we have 2 again and 27. So this 2 cannot be divided. We try to see what can 27 be divided by. Well, it can be divided by 3 and 9. So 9 is also a prime factor, so we cannot divide that. And what can 9 be divided by? Well, that can be 3 and 3. So now we have our prime factors. So our answer, we then line all of these prime factors up into a multiplication form. So 2 times 2, that would be 2 squared, multiplied by 3 times 3 times 3, that equals 3 cubed. So that's how we get our answer. I think that wraps up everything for this video. If you've been learning and enjoying my videos so far, please give a like, subscribe, and share, because it really does motivate me to continue making more videos. And I'll just now gather up on what we've done in this video. So we've discussed what are indices, 4 index laws, how to apply them, and what is prime factorization. I'll be doing a deeper delve on prime factorization and applications of index notations soon in the next video. Until then, stay tuned.